Hello, my name is Henry Elijah Craig, and this is my Physics 2212 Lab 1 report on tape and electric fields. Some general background. Objects can acquire a net negative or net positive charge by rubbing together, being pulled apart from, or even just touching other objects. And we know that any charge must be between the charge of an electron and the net positive charge if every electron was removed from an object, which would be Avogadro's number multiplied by the charge of an electron, which is about 1 times 10 to the fifth coulombs. The goal of this experiment was to use our knowledge of electric fields and electric forces to determine the approximate charge of a charged piece of clear tape. The first major part of this experiment was to determine the sign of the charge of a piece of tape. So by making two charged pieces of tape and holding them near each other, we saw that they repelled each other, meaning they had the same sign on their electric charge because like charges repel each other. Then, using an object we knew the sign of the charge of, such as a plastic pen being rubbed against hair or fabric giving a negative charge, we held this near a piece of charged tape, and it was attracted to the charged tape, showing us that our tape was in fact positively charged. The second major part of this experiment was to determine the charge in coulombs of one piece of charged tape. We did this by weighing the electric force of one piece of charged tape against another against the force of gravity and determining the distance between the two pieces of tape where these two forces were balanced. To do this, we had to make some simplifying assumptions, such as treating each piece of tape as a point charge in our mathematical calculations, with all of the charge being centralized at that point in the center of the piece of tape. We also had to assume that each piece of tape had the same net charge, both in sign and magnitude. In order for us to use this model with our known mathematical equations, we had to know the distance between the two pieces of tape, where the electric force between the two pieces of tape balanced out with the magnitude of the force of gravity. In order to do this, we used a design similar to the one shown here, where you had a piece of tape, tape B in this case, hanging, and another piece of tape, tape A, both charged, being held close to each other until tape B was repelled away from tape A in the upwards direction, where it laid flat and balanced out with the force of gravity. We determined this distance between the two pieces of tape, our separation distance, was about 1 inch or 0.025 meters. With our known values of the mass of the piece of tape being 0.218 grams, which was calculated by the fact that 1 meter of tape is 1 gram and we used 21.8 centimeters of tape, and our separation distance between the two pieces of tape used in our experiment was 0.025 meters. We can use the fact that the electric force on an object is the charge of the object times the electric field present, which would be this constant 9 times 10 to the ninth times the product of the two charges divided by the separation distance squared. Now, since these two charges on each piece of tape were assumed to be equal, we can just use the constant 9 times 10 to the ninth times the charge squared divided by the separation distance squared. And we can set this equal to the force of gravity, which is mass times g, where the constant g is 9.81 in the downward direction. Here you can see that after setting these two equations equal to each other and solving for Q, the charge of one piece of tape, we got the net charge on a single piece of charged tape was 3.85 times 10 to the negative 7 coulombs. The math done by this computational model gave the same net charge, and we were able to see the effects of the electric field and the electric force coming off of piece of tape A onto piece of tape B to help hold it up and allow it to float despite the effects of gravity. Using the assumption that all atoms take up 1 times 10 to the negative 20 square meters, and the fact that they are evenly distributed throughout the whole tape, we were able to come up with an approximate number of atoms for a single piece of tape. And similarly, by dividing the charge of one piece of tape that we calculated earlier by the charge of a single electron, we are able to calculate the number of total electrons lost by a piece of charged tape in our experiment. By dividing the total number of atoms by the approximate number of electrons lost, we found that about 0.0005809% of atoms on the tape lost an electron. To answer some theoretical questions, if electrons had a positive charge and protons had a negative charge, the general ideas in our experiment would still work. Like charges would still repel each other, and different charges would still be attracted to each other, allowing us to gather the same data we did in this experiment. So in the picture of this experiment, the charges flipping would not have any effect on our data, other than the fact that the charged pieces of tape would now have a negative charge instead of a positive charge. And it was important during this experiment to contact the tape as little as possible due to the fact that just as ripping a piece of tape off of another in step 1 of this experiment to create a charge, rubbing it on our fingers and on our hands could just as easily remove that charge from the tape.